Hello, ladies and gentlemen, all you fine folks out there. We're going to continue our look at the 2018 Euclid Math Contest with question number 9 in this video. So the second last question, and we should expect it to be challenging. 8's challenging, 9's challenging, 10 is challenging. These are usually the hardest questions on the contest, and they are almost always required to be purely written. What have we got for 9? An L-shaped triomino is composed of 3 unit squares as shown. So a little L or corner piece, I guess. Suppose that H and W are positive integers. An H by W rectangle can be tiled if the rectangle can be completely covered with non-overlapping copies of the triomino, each of which can be rotated or translated, I guess they say. And the sum of the areas of these non-overlapping triominoes equals the area of the rectangle. That is, no triomino is sort of hanging outside there. So I can't have a little extra bit there. Okay. If such a rectangle can be tiled, a tiling is a specific configuration of triominoes that tile the rectangle. Okay. So, looks like all the parts of this question are going to be connected. A part, draw a tiling of a 3 by 8 rectangle. And just because it looks like all the parts are going to be connected, as opposed to, say, question number 8, where A didn't really have anything to do with B, let's read through the whole thing. That way we get a sense of where we're going. This is something I recommend you often do on questions 10, and really any question that's completely connected, and that's almost always question 10, but I guess they did it for 9 as well. Or maybe they didn't do it for 10. Well, no, I don't know. We'll find out. Okay. So, draw a tiling of a 3 by 8 rectangle. That's fine. That's just, do you understand the concept of a tiling? B part. Determine, with justification, all integers W for which a 6 by W rectangle can be tiled. So the height's being specified for us. Okay. Now, C part, determine, with justification again, all pairs HW of integers with H greater than or equal to 4 and W greater than or equal to 4, for which an H by W rectangle can be tiled. Okay. I wonder if there's a particular reason it has to be bigger than or equal to 4. I mean, maybe the fact that we've got 3 here? I don't know. We'll see. Although, I'm thinking just because some of the triominoes, their areas has to equal the area of the rectangle, I think we'll need to have multiples of 3, at least. Although maybe B part is trying to tell us we need multiples of 2 and 3 to get 6. I don't know. Let's just get into A and do a tiling of a 3 by 8. I think there's not really going to be a particular strategy to this. I think we're just going to play around with it until we find one. I don't think this is worth very many marks. And it won't, in theory, be that hard. Okay, so I want to indicate my tiling to whoever it is. I can't just say, there, I did it. Look at it, it worked. And I seem to recall when we were marking that people did that. So you got to be careful. You got to in some way indicate. I'm going to use color. Some people, I think, used patterns. But I think we can try something like, there's a triomino, and there's the red one, I guess. Then maybe, well, we can just sort of do pairs of this pattern here. So there we go, very colorful. We've got our pattern going on here. And that's a tiling, and that's all we need, is we just needed to show a tiling, so I guess there we go. This is probably worth 2 marks. So there we go. It never hurts to try the A parts of some of the later questions, because they're often very, very simple, basic things. I mean, not when there's 2 parts, but when the whole thing's connected, like 9 is, and I assume 10 is, just trying A part can, or part A of the question, can give you a couple marks, and it's often just a quick, did you understand what we just told you? Okay, so determine with justification all integers w for which a 6 by w rectangle can be tiled. Now, in terms of tiling rectangles, I really like the bit here that we sort of put together. And so I wonder, can we use that? I mean, obviously, I can't tile a 6 by 1 because you'll get overlap. But could I do a 6 by 2? Well, I suppose we could have an L there, and yeah, just 2 stacked copies of this thing. Now, what if I wanted to add in a third layer? Well, again, you'd run into that overlap problem, but who says I have to have the first little bit look like this? So I guess we could instead have, if I wanted to just do 3, we could turn the sort of 3 by 2 on its side, and that will still work. So I guess we can get any even number just by repeating this pattern over and over and over again. And I guess we could get any multiple of 3 just by repeating that pattern over and over again. Could we get other numbers? Well, I suppose we could get 5 just by repeating the 2 pattern and the 3 pattern. So any combination of 2s and 3s. Now, what is that? So, and we've also got to write things up as we do it. So, what's the best way to write this up so it's clear? And also, I still need to figure out what are the possible W's. So we can. So notice we can get W is any even number by repeating the pattern 1, 2, 3, 4, 5, 6. I'll go back to colors. So that L there and that L there, and we'll put the red ones in. So we just need to repeat that pattern. W over 2, because if W is even, we just need to repeat that W over 2 times. And maybe write out an example of it working for W is 2, W is 4, but I would say the pattern is clear. Now, we could also do the multiples of 3, but we can also do things like 3 plus 5. So we can do 3, we could do 5. Could we do 7? Well, 7's different. It's not even. So you'd need at least one of these 3's. And actually, yeah, once you have 3, you're odd, and then what's left over is even. So we can also let W be any odd number. Now, not any odd number, because you can't have 1. So greater than 1. By using this pattern on its side. So one of the 6 by 3 patterns, and then you can just keep doing the 6 by 2 pattern over and over again. So one of the 6 by 3 patterns followed by W minus 3 over 2, which will be an integer because W is odd and it's greater than 1, copies of our 6x2 pattern. So, for example, W could be 7. So here I'll actually do the W equals 7 pattern to show off. 1, 2, 3, 4, 5, 6, 7. Split it in half and split the halves into thirds. There we go. Okay, so what have we got? We need 1 copy of the 3x6 pattern. And then we would need 1 copy of the oops, I did that wrong. That one and that one. And then we need another copy of that pattern. Okay. So there we go. That would be W is 7. Okay. Now, that covers every even number and every odd number greater than 1, so the only thing to close is by saying we can't have W equal to 1. As the width of the triomino is 2, and so there would be overlap. And I suppose we could draw a little picture of overlap happening. Or you could place it like this. Either way, you're going to get some sort of overlap. Okay. So that's a B part. That wasn't so bad. Might have taken a little while. I think if you really sort of do A in a very weird way, you might miss this pattern, but I think if you're just trying to get the pattern out as quick as possible, I think you're going to see this block, and whether or not you make the connection that that block can be stacked to make a 6x2 or a 6x3 might depend how quickly you get B part here. And then, even then, you might say multiples of 2, multiples of 3. You might make the connection combinations of them, but just because you know you can say, well, it's all numbers that can be written as 2x plus 3y. That doesn't actually tell the person who's marking or who's reading what exactly the set of numbers you've got are. You can say what they look like, but really quickly, if somebody says, is 19 in your group, or your set of numbers, you might say, I don't know, let me do some work to see if it's a 2x plus 3y. Whereas the way we sort of walked into it is the evens fall quite quickly. I was going to write multiples of 3, but then 3 and 5 can happen, and asking about 3 and 7, it just sort of clicks that, oh yeah, the odd numbers will work. So all evens, all odds, so any number greater than 1. And actually, I should probably write that down as a summary. So, therefore, W can be any integer greater than 1. That's probably worth a mark, a summary. Although I would argue that it might be clear from what I said, all odds, all evens. But better safe than sorry, eh? Okay, so C part, determine with justification all pairs HW of integers, H greater than or equal to 4, W greater than or equal to 4, that can be tiled if it's an HW rectangle. Alright, I haven't found A and B to be all that challenging yet, so either I'm really good at tilings, or I think there's going to be a bit of a difficulty in C. Okay? So it's a little more open-ended than the 6 by W. 6 gave you some structure. Hmm. Well, suppose we can use K triominoes to tile an H by W rectangle. Okay? I'm going to look for some conditions that need to be satisfied because it turns out just about anything in B could be tiled, and I very much doubt the case is true that anything can be tiled for C. I mean, I'm willing to be proven wrong, but I think there are some things, like number of tiles, surely would have to be a multiple of 3 or something like that, right? Then area of K triominoes, by their definition, means that has to be equal to the area of H by W rectangle. So 3 squares for each triomino, so 3K is H times W. 3 is a prime. So 3 divides HW, and therefore 3 divides H, and or 3 divides W. Now that was fine in B part because, well, we had 6 by something, so we already had that multiple of 3. Now, do we need to necessarily have a multiple of 2? So could I find one where there is no multiple of 2, or is there some reason that I have to have a multiple of 2? I suppose we could play around and try and make a tiling. So B really makes me think that we might need a multiple of 2, and therefore like 6 is somehow in here, but I don't know. Let's try to determine if 2 divides HW. That's not something I would actually want written in a proof. You never say, let's try to. Because you want to be confident in your proof. I don't know. I think I just need to sort of experiment. What would be... You need to have a multiple of 3. 3 by... Oh, wait, no, I can't have 3. It's got to be greater than or equal to 4. So I guess I could have a 5 by 6... 9. I guess I would need 5 by 9. Could this be tiled? And if I run into some troubles here, I would think that maybe we need some even numbers. Okay, 1, 2. Ugh, that's not a good one. That's not a good second one. Okay. Let's break this into thirds. And break each of those into thirds. Okay, that's a 5 by 9. Now let's see what we can tile. Now, obviously, I should try and actually avoid using pairs, because pairs will at some point fail. If this could succeed, I will need an odd number of these. I will need 15 triominoes. But I suppose we could try pairing for a little while, just because it's such a nice structure. Now we're running into some space issues. Oh, that one won't work. That won't do. So let's see if we can play around with some of these other ones. No, that won't work. It could be I am actually trying to do something that can't be done. That is entirely possible. Oh, there we go. Okay. So my experiment, and this experiment was, do I necessarily need an even number? Like, does there need to be a multiple of 2 in there? Because we know there needs to be a multiple of 3 amongst H and W, but there doesn't necessarily need to be a multiple of 2. And I guess this shows that no, you don't need that. Let me just double check and make sure this is actually. Let's shade things in blue. So that's one. That's one. That's fine. I want no. I'm just doing it so it's thicker so that I can really see that no square is left unshaded. I've got 5 there, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. All right, we did it. So a 5 by 9 tiling can occur. But it's not, I'm not noticing sort of an immediate pattern. I think the real important thing here was this sort of piecing together here. I thought that's kind of interesting, and the fact that just sort of popped in there really made it all work. Okay, so a 5 by 9 tiling can be done. Now we could have something like a 7 by 9 maybe, or and do I need to find a 7 by 9, or is there some sort of pattern or some way I can build these up? But at least I know for a fact that you don't need an even number. So the question now becomes, do I just need a multiple of 3? Is that it? Is that the bare minimum? Do I just need a multiple of 3? And if that's my belief, then I guess we need to start trying to prove that. And if I don't think that's the case, then where might the failing occur? I mean, I've got a 5 by 9 here, but what if I want to do something like a 5 by 15 or a 7 by 15, because there's only one multiple of 3 there. I mean, the 9 here is giving me an extra 3. Is that somehow causing an issue? Or causing me to get more than I think? All right. Well, I know that if uh, 6 is equal to H, or okay, if okay, I think we need to do some cases. I'm just not entirely sure what cases. I want to use B part. So I think right now we're going to say we claim that H by W can be tiled if and only if one or both of H and W, wrote H and H, didn't I? H and W is a multiple of 3. Now the challenge is going to be, well, how do I show that? And I think in the process of showing that, because here's the way we approach the question. I think this is sort of a good sort of teaching moment of how to approach a question. We looked at some theory at the start here with this 3K, and We said 3 must divide 1 of h or w. Guarantee. And then we compared back to b. Now in b part we had 6. 6 was always a multiple of the height. And so that got me thinking, well, could I have a multiple of 2? So I tried to show that that must be the case by playing around with 5 by 9, which is the smallest situation where you wouldn't have a multiple of 6 kicking around. Or not even a multiple of 6, but just having a factor of 2 in h and w as well. Okay? And it turns out that that was fine. So the thing that I thought was going to cause me the most problems turned out to be fine. So now I change my thought and think maybe we have the most lenient of possible situations. And we're going to explore this. And if we run into problems, we'll come back and revise this. And it'll turn out, you know, you need to have a multiple of 3 and 2 or 2 multiples of 3, for example. And that would explain the 9 I saw a little while ago. But we're going to start with this, and we're going to progress. And I think some cases are in order. Okay. So, we'll prove this by cases. Okay. So, in the if and only if, the only if is already taken care of, as we proved. 3 divides h or, well, and or. 3 divides w. We already said that. So now we do the if. So if, we will prove by cases. Alright, so here's case 1. Actually, here, let's make a little statement. But before we do, we'll assume 3 divides h as the 3 divides w cases can be handled by flipping the rectangle. And what I mean by that, in B we proved that you can do a 6 by 2. So obviously you can do a 2 by 6. You just flip it. Okay. So now this will make writing the cases out a lot easier. So case 1, 3 divides h and 2 divides h. So that tells me 6 divides h. So let h equal, I already used k, so let's say 6n. Or 6 little h. 6 little h looks nice. Since w is greater than or equal to 4, we saw in B that 6 by w can be tiled. So just stack h copies of that tiling. That's all it is. Because if I want to do 12 by 4, like a nice big dividing line here. But I'm just going to do, we'll use pink. Just going to do what I did earlier, except I just changed my pattern there. So you just repeat the pattern, And you just put it in the same place and just translate it up as many times as you need it. Okay. So that's what happens if you got 3 and 2. So now what I'm going to do is case 3 divides H and 2 doesn't divide H, but 2 divides W. Okay, so we've got 3's and 2's. So let's say let H be 3 little h and W be 2 little w. By using H W copies of my 3 by gotta make sure I get the height right. My 3 by 2 block, the very first thing we sort of noticed in this question, we can tile the H by W rectangle. So, for example, if I have a height of, I don't know, 9, it's going to be a bit of a pain to draw, so we'll make this a little bit bigger. So 9 by, I don't know, 4 will probably do the trick. One, 2, 3, 4. Okay, so what are we going to do? Well, just do 3 copies of this. I'm going to color code them just so it's nice and visually distinct. But there we go. So that's as an example. But you just need HW copies because H of these gives me the height 3H, and W of these across gives me 2W. Okay, so that's not bad. Now, case 3. I have been numbering my cases, right? No, I have numbered case 1. I did not number case 2. Now we got case 3. So 3 divides H. 2 does not divide H or W. So a nice quick way to say that is 2 does not divide their product, because 2 is a prime. So, okay, so now what can we do? I know that the 5 by 9 worked out. But what if it's something bigger? What if it's something like a 7 by 9? Well, So, we know we can tile a 9 by 5. So, well, I think of how I want to... I think what we're going to have to do... So what we've been doing so far with our cases is basically saying, here's how to take a simpler tiling and build the whole thing up. And again, these dimensions are too big for me. So I think we're going to have to do that, but it's not going to be just a bunch of 5 by 9s sitting around. think we're going to need to use this sort of as a nugget or a starting point, like so that's 6, 7. Oops, that did not turn out well. And we're going to build off of this, but not using copies of itself, but I think the 3x2 blocks will come in and save the day again. Alright, just to prove it's not a fluke, let's see if we can redo this. So, if I have trouble, I will go back and just look it up. Let's try and go around the outside here. Okay, that didn't quite work. That one has to be there. So let's get rid of that one. No, that has to be there as well. I suppose I could flip this one around. Yeah, there we go. Much easier this time. Alright, so there's my example of doing a 9x5. Now, suppose I wanted a 9x7. Well, I would just add on... so we can do a 9 by any odd. So W is greater than or equal to 4. So if W is odd, W equals 5 plus 2 little w's. And if it's not the 5 case, if little w is greater than or equal to 1, then we can make a 9 by w by adding on 9 by 2's. Well, we don't know that we can make 9 by 2's made of 3 stacks, so we'll have to describe that. 3 stacks of our 3 by 2 building block. Okay, so what would that look like? So we get our 9 by 5 that we know we can do. And then we'd have W copies it's very hard to draw straight lines freehand. One, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. I'll have 1, 2, 3, 1, 2. Switch it over to red. And down to green. So now I can do 9 by any odd. I think then if H is odd, 3 divides H, and H is greater than or equal to 4, then H is equal to 9 plus 6 little h. And if little h is greater than or equal to 1, we can make an h by w, w also odd, greater than or equal to 4. And here's how we do that. So up here we have 9 by W, which I just showed can be made. And so we will, so by stacking H copies of 6 by W, which we know we can make. So I will have, there's a 6 by W, and all the way down to the bottom we'll have 6 by W's. H copies, and I know I can do 6 by W because that was my first case. 6 by W's. So we know we can make, because that was case 1. I suppose this could be technically case 5 and this last one's case 4, but I think it's all really under the heading of odd cases. But you break it down as you need to. Okay, so those are my 3 cases, maybe technically 5 cases, but I think we've got everything. Because what have we got here? We've got, so we're assuming H is divisible by 3. Of course, if we want a W divisible by 3, we can flip things. But so H divisible by 3, but then we have options. Either none of the numbers are odd, or none of the numbers are even. So H is even, cases are done. Doesn't matter if W is even or not. H isn't even, but W is. That's dealt with. Or they're both not even. And that covers all possibilities. And we know we have to at least have a multiple of 3 in there. So I think taken together, these cases prove what we want. Which means we're done. All right, so that finishes off question number 9. I suppose I could put a little therefore statement saying these 3 cases cover all possibilities. And I'll just list them out again. H even, H odd but W even, H and W odd. And that does it. So we are all done. And that finishes off question number 9. Up next will be question number 10. And oh, look at that. Lots of words and some array. But we'll get to that in the next video. So I will see you for question number 10 on our 2018 Euclid next time. Until then, take care.